Krishna, yeah. So if you see this part of the handout, here we have basically added the different concepts of sum of squares. Now, in one of the classes, graphically, I had shown that the total sum of squares, it can be decomposed into two components. One is the explained part. Explained part means the part of the variations in the dependent variable which is explained by the estimated model. And this part is known as explained sum of squares. Okay. And the other part is basically the remaining variations in y which is not explained by the regression model. In one of the classes, I discussed about the importance of understanding this decomposition. And for that, we need to get back to the very basic idea behind regression analysis. What we try to do here, suppose I have a sample of 100 households. I have collected data on, say, their consumption expenditure and their income. Now, for these 100 sample households, there would be an average income and individual household income will be deviating from that average income. Question is, to what extent such deviations from the mean is because of differences in income or variations in income. So in regression analysis, we basically aim at understanding why there is a variation like this. Variation of y from its arithmetic mean. Deviation of y from its arithmetic mean. Why there is a variation in consumption expenditure? To what extent it is because of income? In regression analysis, we basically try to answer some such questions. Now, this total variation, partly if I consider only one explanatory variable, that is income, and if there are, say, for example, some other factors what I don't consider in this particular model, then obviously a part of the variation would be explained by differences in income and a part will remain unexplained. Now this unexplained part may be because of various reasons. It may be because of exclusion of some variables. It may be because of wrong functional form that I have picked up. So there may be various reasons. Two concepts are very, very important here. One is the decomposition of total sum of squares into these two components, the explained sum of squares and the residual sum of squares. And the other important aspect of it is the corresponding degrees of freedom. This part, this degrees of freedom, this component, this aspect, right now I am not focusing on that. I'll get back to that concept later on. But what is very important in regression analysis is to understand to what extent the estimated model can explain the variations in the dependent variable. And that is basically reflected in the value of R square. What is R square? By definition, R square is explained sum of square divided by total sum of squares. So you see, total sum of squares, I am just giving the abbreviation TSS, and explained sum of square, that is ESS. So R square is nothing but ESS divided by TSS. So it basically represents the proportion of variation in Y, that is the dependent variable, which is explained by the estimated model. And higher the value of R square, it is generally said better is the model, because higher the value of R square means larger part of variation in the dependent variable is explained by the estimated model. So there may be a tendency to select a model where the R square value is very high. But again, as we discussed in some of the classes, there may be some adverse consequences of simply aiming at raising the value of R square. I told you that neither a very high value of R square can reflect that this is the best model, nor we can necessarily discard a model where the value of R square is very low. There are many issues that we need to discuss. One simple aspect I was telling you in one of the classes at the beginning, that a very high value of R square and say hardly any individual coefficient is statistically significant, that basically reflects or that signals, I would say, the possibility of severe multicollinearity. Again, in regression analysis, multicollinearity problem is a typical problem which can have some consequences on the OLS estimators. Again, we'll discuss on that when we discuss on the issue of multipolarity. But essentially, this R-square value is an important indicator, definitely, of suitability of a model, how good the estimated model is, and that is why this R-square value is also known as an indicator of goodness of fit. Okay, so by definition, it basically represents the proportion of variations in the dependent variable which is explained by the estimated model. Okay. Now, if we just get back to these concepts of explained sum of squares, say for example, it basically represents the sum of the square of the deviations of the sample regression function from y bar or y hat bar, you can say, because we know that y bar is equal to y hat bar when summation of u hat I is equal to 0. Now, for a bivariate model, what we can write? We can write that for a model like this, y hat I is equal to this and y hat bar is equal to this, and then this explained sum of squares, it can be rewritten as beta hat square into summation of small xi square. Now, what is residual sum of square? Residual sum of square is basically the sum of the squares of deviation between yi and y hat I. So it is basically summation of u hat I square. And total sum of square, as I have already discussed, it is basically summation of square of deviations of y, that is the actual observation of y from its arithmetic mean. Now, I can show that this sum of squares, this total sum of squares, it can be decomposed into explained sum of square and residual sum of square. Already we have discussed by using the graph, and this detailed derivation is given here. What basically we need to do? Set total sum of square. We have this as total sum of square. So what I'm doing here, I'm just subtracting y hat I and I'm adding y hat I. Then I am having a plus b whole square. So a square plus b square plus 2ab. Now, using that graph, we had discussed that these two components are actually disjoint. These two components, they are actually disjoint. And hence, you will see this as 0. And the detailed derivations are given here with the respective conditions. So basically what we need to do, this is u hat I. So if you just write u hat I here, then this component can be rewritten as 2 into summation of y hat I into u hat I minus 2 into y bar into summation of u hat I. Now summation of u hat I is equal to 0. That we get when we differentiate partially summation of u hat I square with respect to alpha hat. And this already again we have derived that this is also equal to 0. So this component would be equal to 0. So we are left with these two components, and you know this is RSS and this is ESS. So total sum of square can be decomposed into explained sum of squares and residual sum of squares. Then there are some other concepts like.
So can you explain the y u hat I and y hat I product summation
This
of
one,
u hat?
are you talking about this?
Yes, sir.
This already we have derived here, no? If you see, you see this component. So u hat I into y hat I. So what we are doing? We are replacing y hat I with alpha hat plus beta hat xi. Then alpha hat will come out of the summation, we will be left with u hat I plus beta hat into u hat I capital Xi summation. Now you have seen earlier that summation of u hat I is equal to 0, summation of u hat I capital Xi is equal to 0. So this is also equal to 0, this is also equal to 0. Hence summation of u hat I capital y hat I is equal to 0.
Okay, got it. Thank you.
Is it clear?
Yes, sir. Yes, sir.
Okay, so now we have total sum of square. It can be decomposed into residual sum of square and explained sum of squares. Then there are some other concepts like mean of explained sum of squares, mean of residual sum of squares, and mean of total sum of squares. These are nothing but the respective sum of squares divided by the respective degrees of freedom. So when I say mean of explained sum of squares, it is basically explained sum of squares divided by the respective degrees of freedom. Now again, as I said, I mean degrees of freedom, this concept I'll discuss little later because it requires some understanding of other part of statistics. So I'm not just focusing right now on that. But again, I'll get back to that. So mean of residual sum of square, again, residual sum of square divided by respective degrees of freedom. Okay, and same is for total sum of square. Now this R square, right? For a bivariate model, this R square value, which is nothing but the ratio of explained sum of squares to total sum of squares, this can be rewritten as this. Because for a bivariate model, already here we have derived that ESS is equal to beta hat square into summation of small xi square. So if you just replace, I can rewrite it like this. Now there are two very important questions. What we have proved empirically in one of the classes, I think in the last lab class, but let us see it mathematically. One is, for this bivariate model, this capital R square is nothing but small r square, where small r where small r is nothing but the pairwise correlation coefficient between x and y. And we need to prove this. So what we are doing? We know that for this bivariate model, r square can be rewritten like this. And we know that beta hat is equal to this. Already we have derived this. So capital R square can now be rewritten as this into this is the formula for beta hat and then beta hat square. So beta hat square into this component. Now what will happen? You can see in the denominator here, I will have summation of small xi square whole square, and here I have summation of small xi square. So one would be cancelled out. So what I can do, I can rewrite this as summation of small xi yi divided by square root of summation of small xi square, summation of small yi square, and then whole square. And you know this is nothing but the formula for correlation coefficient between x and y. So this capital R square is nothing but small r square, but this is true only for a bivariate model. For a multiple regression model, when we have more than one independent variable, this relationship will change. Again, we'll discuss that, we'll prove that in the class, how this relationship between pairwise correlation coefficient and this capital R square or goodness of fit, how the relationship between these two will change when we switch over from a bivariate model to a multiple regression model. That would be very interesting. Okay. But for a bivariate model, this capital R square is nothing but small r square, where small r is nothing but the pairwise correlation coefficient between x and y. At the same time, empirically we had seen that the multiple r, the modulus of multiple r is equal to the modulus of small r, that is the pairwise correlation coefficient between x and y. And you know this is multiple r. That is the correlation coefficient between y and y hat. And you know the logic that y hat I is nothing but a linear transformation of xi. So this is the formula for multiple r, and you just need to replace y hat I here with these two. That is y hat I is equal to alpha hat plus beta hat xi, and y hat bar is equal to alpha hat plus beta hat x bar. So we need to just replace, and then through mathematical simplification you will be getting an expression like this. Now in the denominator, because we are taking it out of the square root, we are basically treating in respect of standard deviations, we are basically treating the positive value that you know. So it all depends on the sign of beta hat. If beta hat is positive, they would be the same. If beta hat is negative, then one will be just the negative of other. So in general, we can say the absolute value of the two correlation coefficients would be the same. But again, this is true for a bivariate model. Okay. The third important aspect is that how the regression results may change. if we change the origin and scale of the variables. So let us change the origin and scale of x by a and b respectively. So I am defining the new variable as xi star, which is equal to a plus b xi. Similarly, I am changing the origin and scale of y by c and d respectively. So yi star is equal to c plus d yi, and accordingly we will get the arithmetic means, that is x star bar is equal to a plus b x bar and y star bar as c plus d y bar. My question here was, how will such changes in origin and scale of the variables would affect the OLS estimators of alpha hat and beta hat, and also the value of R square. Now, what we are getting from here, since we are changing the origin and scale of the variables, their respective arithmetic mean will also change, and hence I can write small xi star as this, which will be nothing but b into small xi. Similarly, small yi star would be equal to d into small xi. Then beta star, that is the new estimator, the new OLS estimator of beta, would be equal to summation of xi star, small yi star divided by summation of small xi star square. Then you replace all these and you will get an expression like this, which will be d by b into beta hat. And similarly, alpha star is equal to y star bar minus beta star into x star bar. So I'm just replacing y star bar with c plus d y bar, beta star with d by b into beta hat, and x star by a plus d x bar. And then again through mathematical simplification, we can write it as theta plus d into alpha hat, where theta is nothing but this component. Okay. Now, what is happening? Here we can see that both OLS estimators of both the coefficients, that is intercept as well as the slope, both are changing, but there is no change in R square value. You can see R star square is equal to R square. Just to replace the respective formulas, expressions, you will get capital R star square as R square. There may be some related questions also, like how will the variance of alpha, OLS estimator of alpha and beta, how their respective variances will change. All these derivations we will do subsequently. But what I'll do now, I'll stop here. Before I go for subsequent discussions on these questions, let us just switch over to the empirical part. Now, by this time, I understand that earlier you were not aware of many such concepts, but we have already discussed. And I had shared a data sheet with you in the last week. So let us do some empirical work in connection with these concepts, like say, let us try to get alpha hat. Let us try to get beta hat, capital R square, ESS, RSS, TSS. Then how the estimates will change if we change their original scale. Let us try to revisit these concepts by using some data. And in next half an hour or so, let us focus on that part. And once that part is done, we'll again get back to the discussions on these questions to have further clarity on different concepts and derivations that we have done so far. I'll stop here and